Citadel Civil Engineering program. This is CIVL202 statics. And in this lecture, we're going to be talking about 3D vector systems. Just as a reminder, statics is building upon concepts that we've learned in the past to equip us to do analysis and design in the future. This lecture in particular, focusing on 3D, is not something we're going to use a lot in statics itself. We're going to master concepts in 2D mainly. But in the future, you'll need 3D as you're working in a three-dimensional world. And so three-dimensional concepts are very important. In this lecture in particular, we'll be working on the 3D visualization skills, hopefully you practiced and began to develop in your engineering drawing class, and then translating them into vector mathematics using trig to do so. Again, this is about equipping us to be able to do the particle equilibrium and the rigid body equilibrium that is the main focus of statics. And so again, we're setting ourselves up to do that. Now, in order to do so, we need to start by thinking about what a right-handed coordinate system is. This is our traditional Cartesian coordinate system. I imagine it's familiar to many of you. The idea here is that we're going to have three axes. So again, I'm trying to draw in 3D. Typically, when we draw it this way, we put our z-axis in the vertical direction, and then our x and our y-axis. We use our right-handed rule where we take our right hand. This is where I'm very jealous of my left-handed students, because you can keep taking notes and use your right-hand rule at the same time. For those of us who are right-handed, you'll need to put your pencil down in order to be able to pull out your right-hand rule. So what we'll do is we'll start with our index finger. This is going to be our x direction, in this case out of the board. The middle finger becomes our y-axis, and then our thumb gives us our z-axis direction. So this is your engineer's hand sign. When you recognize another engineer on the street, you can throw your right-hand rule and they'll know what you're talking about. So there's our right-handed rule in 3D. Now, if we think about it in 2D, we're used to drawing our x and y axes like so, x and y, which means that when I use my right-hand rule, x, y, z, my z-axis is now coming out of the board. So if we were to draw this as a unit vector, we would actually have the arrowhead coming out of the board. Now, since I mentioned unit vectors, we're familiar with the idea of our unit vectors, one long, I in the x direction, and j in the y direction, I and j. Should not surprise us that we have the unit vector k in the z direction, I, j, k. And just for the sake of comprehensiveness, we'll note that our I unit vector has a magnitude of 1 pointed in the x direction. This is really connected down to this diagram. Our j unit vector has a magnitude of 1 pointed in the y direction. And our new k unit vector has a magnitude of 1 pointed in the z direction. And what you'll see that I've drawn here is actually the arrowhead coming out of the board directly at us. Okay, so this sets up our base way of thinking about this. This is our right-handed coordinate system. You can see the picture from your book there. So we've just covered our right-handed coordinate system. And now what we want to do is think, how do we apply this right-handed coordinate system to a vector itself? And the most natural way to do this, if we've identified our unit vectors, is actually to use our Cartesian vector notation to perform this analysis. So if I have some general vector, vector A, my Cartesian vector notation tells me that I'm going to have x, y, and z components, like so, which you can see in the diagram on the left with my x, my y, and my z components, which if I add them together using tail-to-head addition, I'll end up with my vector. And so if I look at a 3D model, here's my x-axis, right-hand rule, so x. Here's my y, that's where my middle finger is pointing. And then my z is straight up. Here's the vector that I'm interested in. We'll also notice that I can have those unit vectors, I and j and k, one in each direction. And now I have my vector where I'm projecting back and I'm getting the x plus the y plus the z component, tail to head, brings me up to my overall vector, like so. So this is my Cartesian vector notation. Now the important thing to recognize here is that to fully identify a vector, we need three components. So we're going to have our x, our y, and our z components, like so. And so with those three components, I know everything there is to know about vector A. Now, we might ask the question, well, just how big is vector A? Maybe I'm not so worried about the X, Y, and Z components. I want to know the overall length. So if I'm looking at this diagram over here, I might have my X, Y, and Z, but I want to know what the overall magnitude is of A. When we're working in 2D, we use Pythagorean theorem to do that. And here we're going to do the same thing. So we're going to extend our Pythagorean theorem by doing square root of the sum of the squares of the individual components. So the x component squared plus the y component squared plus the z component squared is going to give us our overall magnitude. So up here I have an expression. Three components fully defines the vector, but if I wanted the magnitude, I now have an equation that would let me solve for the magnitude. If I have the magnitude, that's fantastic, but what I really want as well, every vector has both a magnitude and a direction. And so if I'm going to solve for the direction, it turns out there's a lot of ways that we can talk about that in 3D. The first way we're going to talk about is the unit vector. The unit vector. And we're going to use the symbol mu with a little hat. The idea is that we've still got I, J, and K. Those are the X, Y, and Z components, but my unit vector mu is now going to be, so X, Y, Z. My unit vector is one long and pointed in the same direction as the vector. And so remember that the magnitude is going to be 1 for a unit vector, and we're going to keep the direction only when we think about this unit vector here. So as we think about this, we want it to have a magnitude of 1. And typically, if we have a given value, to solve for the magnitude of 1, or to get a value of 1, we would divide it by the same value. So this would give us a value of 1. But in this case, we want to keep the direction piece. And so we're going to take our actual vector now, with its little arrow hat, and divide it by the overall magnitude. We're going to divide it by the magnitude. And this is going to give us our unit vector, like so. Now, if we recall, we can take this and this 1 over a, well, this is just a scalar value. And if we plug in our Cartesian vector notation, substitute it in here, we'll have our ax in the I, plus ay in the j, plus az in the k. So my x, y, and z components. Well, remember, if we're doing scalar multiplication, we can just multiply the number straight across by the magnitude. And so when we do this, we'll find our unit vector to be ax divided by a in the I direction, plus ay divided by a in the j direction, plus az divided by a in the k direction. Each one of these will be a value less than or equal to 1. That'll give us our unit vector. And after we've done that mathematics, we'll end up with singular, probably decimals or fractions, that give us the unit vector components in the x, y, and z direction, like so. Mu x, mu y, mu z. Now, if we think about the unit vector, remember that the magnitude is equal to 1. So now I have a vector with 3 components that if I wanted to find the overall magnitude, I would do square root of the sum of the squares. And so I'd come in here and I'd say the x component squared plus the y component squared plus the z component squared. Well, that's going to be equal to 1 squared, right? Now, we'll recall that 1 squared is just 1. I could square root both sides. That gives me Pythagorean theorem. But if it's just 1, this becomes an equation that if I know the x, y, and z components, I can double check my work. I can sum up the squares and find out if it's equal to 1, because 1 squared is equal to 1. Alternatively, if I know the magnitude and 2 of the unit vector components, I can use this equation to solve for the third unit vector component. Because again, to define a 3D vector, I only need 3 values. It can either be the x, y, z components, or I can have the magnitude and 2 of my direction components. I can then use this equation to solve for the third component. So that's pretty cool. So there's a lot of good things that we can do here. So this gives us our unit vector piece, and that's what you're seeing here in this middle diagram, where we have the magnitude and the unit vector right like so. So if we've solved for the magnitude and the unit vector, we can now express our overall coordinate system, our overall vector, not only as a Cartesian vector notation, but we can express it as a magnitude A times its unit vector, like so. This would expand back out again if we wanted to convert back into Cartesian vector notation as this. And so again, I could take that magnitude, multiply it by each of the components, and I will get my Cartesian vector notation back. So this is my magnitude and unit vector expression of a vector. Now, turns out that there's yet another way that we can talk about the direction. So if we have the magnitude, we can also think of the direction in terms of the coordinate direction angles, sometimes called the coordinate direction signs. So the coordinate direction angles, coordinate direction angles, what these are doing is that they're looking at the vector and they're thinking about it in terms of a 2D plane. So the coordinate direction angles are going to do a 2D plane. So in order to do this, we need a sketch. And so what we're going to do is we're going to draw a section of the vector in 2D. So there's my vector A, and this is my x-axis, like so. And that means that I'm going to have a component here, AX, and this angle is my coordinate direction angle. Your book uses the notation alpha. The FE reference handbook uses the notation theta x. So if we look at this, does anybody see the right triangle? There's a right triangle there, right? So what we can do is if we look at this, we'll notice that the sine, because it's, the cosine, the coordinate direction cosines, the cosine of that alpha, or the cosine of theta x, is going to be equal to the adjacent ax divided by a. And so that's kind of a neat thing. If I know ax and I know a, I can do the inverse cosine to come up with the answer there. Now, you might be saying, Dr. Wood, that you've drawn some math on the board, but I don't quite see this 2D slice that you're talking about yet. Well, let's look at our 3D model that I have right here. Okay, so again, we use our right-hand rule. Here's my x-axis. Here's my vector. Now, what I'm doing here is I'm drawing a 2D picture, Now, let me see if I can adjust my vector a little bit. Okay, a 2D picture of my vector and the x-axis. So that's what I've drawn a picture of. So here's my x-axis, here's my vector, and here's the angle that I'm looking at. So this is my alpha, or my theta x. This is my coordinate direction angle to the x-axis, and then I'm projecting down to the x-axis to get my ax component. So there's my cosine. Now, one of the other things you'll notice, have we written ax over a on the board before? What about down here? Turns out that mu x, that is the cosine. So again, if we have the angle, we can just take the cosine and we'll get our mu x component. Or if we know the x component in a, we can solve for mu x using inverse cosine. Or if we know the angle and the overall magnitude, we can get that there. Now, turns out we can do the same thing again. Now let's look at the y-axis. So I've got my overall vector A. I've got my AY component pointed in the y direction. I have this is beta or theta y in our FE reference handbook, theta y. In this case, we'll see that the cosine of beta or the cosine of theta y is going to be equal to my adjacent component, AY, divided by A, which we'll notice is the same as my mu y unit vector component. And we can do the same thing in the z direction. and alpha, beta, gamma, or theta z. Cosine of gamma equal to cosine of theta z equal to az divided by a, which is equal to our z unit vector, mu z. So if we look back at our model again, just to make sure that we're getting the pieces all pulled together for our coordinate direction angles, if I have some arbitrary vector, I can draw three separate planes, okay? So here's my 2D, here's my x-axis to the vector. That's a 2D plane with a coordinate direction angle alpha or beta. Over on this side, I have my y-axis and a 2D plane to the vector with my beta or theta y coordinate direction angle. And then if I look at it from this side, I have my z-axis and the vector, so 2D. There's my z direction, coordinate direction angle, so that'd be theta z or gamma. All right, so that gives us these components here, coordinate direction angles. And what this means is, again, I have my ax, my ay, my az, so I can think of my unit vector as simply the cosine of alpha I plus the cosine of beta j plus the cosine of gamma in the k direction. That would give me the unit vector. That's just substituting in these relationships that I've seen, right? So that would bring me back to the unit vector. Or I can think of it in terms of the vector itself. That'd be fine. If we keep in mind, what's the magnitude of the unit vector? It should be 1 long, which means that I can also substitute these values into this equation. So cosine squared alpha plus cosine squared beta plus cosine squared gamma means that if I know two of these angles, I can actually solve for the third using this equation here. So that gives us our coordinate direction angles. So if we were to talk about this as a whole, we would say that we could express the vector A as its magnitude, its alpha, its beta, and its gamma, or A times cosine alpha I plus cosine beta j plus cosine gamma k. And I've kind of run off the board a little bit there, but that's okay. I think we can manage this. All right. So now I've got my Cartesian vector notation. I know how to solve for my magnitude. I know how to solve for my unit vector, like so. It gives me my magnitude and my unit vector. I can also think about my coordinate direction angles. We notice this has 4 terms here, but how many do we actually need to solve for a vector? We only need 3 terms. And so the idea is that if I have the magnitude and 2 of these angles, I can use this equation, where the magnitude of the unit vector is equal to 1, to solve for my last unknown. So I have my Cartesian vector notation. I have my magnitude. I have my unit vector. For my unit vector, I've got my coordinate direction angles. Life feels good. Got one more term that we want to express. And so our last term that we want to express is transverse and azimuth. Again, what we're doing is we're practicing the art of taking 3D visualizations and turning them into our math. So if we're thinking about transverse and azimuth, these angles are going to be theta and phi. This is very much like we would think about in orienteering or in some sort of map and compass type exercise. It is a military college, so I like to use the example of a mortar. So when we think about how we aim a mortar, there are 2 components to aiming a mortar. The first component that we're going to do is going to be from the z-axis. Now, naturally, you don't want to shoot mortars straight up because they tend to come back down, but rather you would set an angle that would give you the overall range. And this angle, by the way, we've talked about it already, that is my gamma or my theta z. Well, we call this angle the azimuth angle from the z-axis. And so when we think about it in those terms, our sketch looks very much like this sketch. So I'm going to have my Z component here. So there's my AZ, my Z indicated. Here's my overall vector A, like so. And this angle here is going to be my azimuth angle. The thing I'll note is that theta z or gamma is equal to phi, which is going to be the same as az. Whoop. We do the inverse cosine of az divided by a, like so. Inverse cosine. So that gives me my azimuth angle, azimuth. Which means that if I know gamma, I can just say gamma or theta z is equal to the azimuth angle. Now the transverse angle describes which direction we point our mortar. So with our mortars, not only is it important that we get the range right, hence my azimuth angle, we also make sure it points in the right direction. Typically the way we'll do that is we look at it in a plan view. So in plan view, we're now looking at it from the top. So if I have my x, y, z, so x is here, y, and then z is coming towards you now, we'll see that in the plan view, I have x and y, and now I have my vector projecting back onto that plane. So I'm looking at the xy plane and I'm projecting back onto that plane so that I can break those components into the x and y components. So when I do this, this is the tricky one. What I've got on this diagram is actually the xy component, because I'm looking at the xy plane there, right? And then I'm going to take this plane view and look at it so that I have the y direction here and the x direction here. And what I'm seeing from the top is not the whole vector, it's this axy component. And this angle here, that's my transverse angle. That's my theta. Now, if I look at this, I'll realize that my theta, or my transverse angle, is, see, opposite over adjacent. So I can actually say the inverse tangent of AY over AX, like so. Or I can think of it this way, where what I'm looking at here is thinking about, okay, well, I have AY over AX. That's fine. That's good. I like that. But I need to know what this AXY is. Well, if I look at the AXY is going to be equal to A times the opposite. So the A times the sine of phi, the sine of phi, of my azimuth angle. So that gives me the projection onto the xy plane. If we look at my diagram here, what we're seeing is that if I use the sine of phi, I'm projecting down. Your book calls it A prime. I'm calling it AXY, like so. So we're getting that magnitude there. Then I can look at it from the top like this, and I can break it down. So if I know AXY, my AX is going to be equal to AXY times, that's adjacent, so cosine of theta, or A sine phi cosine theta. So hopefully you're getting a sense of all the ways that this can be broken down. We're seeing how we're able to pull out this piece. Now, there's a lot going on here in terms of the trig. If I think about AY is going to be equal to AXY opposite, so sine of the transverse angle, or A sine phi times the sine of theta. What this means for us is that if I'm thinking about my overall vector A, I can think of it and describe it in terms of its magnitude, the transverse angle, and the phi angle, three components, yes? And I can also express it back into Cartesian vector notation by looking at A. So I'm collecting my magnitude terms. My x component is going to be first xy, so sine of phi times the cosine of theta I plus, I'm doing some line wrapping there, plus the sine of phi, that gives me my AXY sine, and then AXY sine theta gives me my J component, plus AZ, which is going to be the cosine of phi in the K direction. So that's my third way, or fourth way actually, of describing these things. So I can have my Cartesian vector notation. I can have my unit vector notation. I can do my coordinate direction angles by taking the inverse cosines of the unit vectors. And I can also draw some sketches out to plot my transverse and azimuth direction angles. This is easily the hardest lecture possibly in this class. And so if you're confused, that's okay. We'll work an example problem together in class. So come with those questions ready. And that's what we have for you. Thanks for hanging in there. I'll see you in class.